Okay, what this video is going to cover is 1.4 continuity and one-sided limits. We are going to determine continuity at a point in the continuity on an open interval. Then we're going to determine one-sided limits and the continuity on a closed interval. Use properties of continuity and understanding use the intermediate value theorem. So the first thing we have to do is talk about continuity. And we've used these words ever since we started with limits. When we talk about limits, we said that the function is discontinuous. So we have a place in the graph where we have either a hole, an asymptote, or jump, something like that. So this first one, in the picture showing, is a place where the graph, if I asked you the value at C, you would tell me the value at C is undefined. So f of C would be undefined, and that means that the graph has a break, which means it's discontinuous. That is called a removable discontinuity. The second graph shows a picture where when I approach the C from the left, it approaches one number. When I approach from the right, it's approaching a completely different number. So the limit as x approaches C does not exist. And that's an example of discontinuity. That one either creates an asymptote or a jump. The third thing that can happen is f of C is defined, like f of C, she wrote that wrong, f of C would equal whatever this number is. Let's say that's 3, and up here, let's say this is 5. F of C would equal 3, so f of C is defined. That the limit as x approaches C of x is going to be 5. So since the limit and the C don't equal each other, then it is discontinuous, and that is also a removable discontinuity. And anything that looks like this, where it's not removable, where you have a jump or the asymptote, is a non-removable discontinuity. So going through the definitions of continuity, these three things have to happen. F of C has to be defined. That takes care of this situation here. The limit of f of x exists. That takes care of this situation here, where the limit did not exist. And then the limit of f of x as x approaches C has to equal f of C. And that's, we take care of a situation like this. If all three of those things happen, then that means f of x is continuous on that open interval from A to B, or something, or it's continuous over the entire set of no numbers. I was going to draw this again, but I don't see the need. Find x values of any for which the function is not continuous. So what I do is I look at this, and I can graph it, or I can think about it. This is the shape of a parabola. And when I think of the shape of a parabola, I'm thinking about its domain. And if I ask you what the domain of this is, you're going to tell me the domain. What I can put in brackets is all real numbers, so negative infinity to infinity. I'm not going to have any breaks in this graph. I'm not going to have any jumps, asymptotes, anything like that. So this will be a continuous graph. The next one is I have this x minus 25 over x plus 5. If you graph it on your calculator, it's going to look like a straight line. You have to be very careful with this. Remember that the numerator can factor as x plus 5, x minus 5, and my denominator is x plus 5. So these x plus 5 simplify. And so when you graph it, you're going to get a graph that appears to be the line x minus 5. The only place that it differs is at the point of negative 5. So here my domain will be all real numbers, except x cannot equal negative 5. X cannot equal negative 5. So I do have it, so it is discontinuous. Graph is discontinuous at x is equal to negative 5. But since it simplifies and it gives the same graph as another function that is continuous, I'm going to say it's a removable discontinuity. The last one, I have a graph of 1 over x. I can graph it. If you graph it on your calculator, you're going to get something that looks like this. It's actually you should recognize that shape as a hyperbola, rotated. Since when I approach it, so when I take the limit as x approaches 0, I'm going to say that that limit does not exist, because as I approach from one side, It's positive infinity. As I approach from the left side, it's negative infinity. So my limit does not exist. I can't fix it by substituting anything in or simplifying. So since the limit does not exist, it's discontinuous at x is equal to 0. And since I cannot fix that discontinuity, I cannot simplify, I cannot rationalize the numerator or anything like that to take care of it, I'm going to say it's non-removable. Remember, that's removable. Remember, when you look at the graph, if it's something that you can't simply plug into, then it's going to be a non-removable discontinuity. If it's a graph that has like a hole that you can sort of just plug, then it's removable. And here are some examples. If I give you this one, that's the one we just did. This would be non-removable. So it would be non-removable discontinuity. We're just going to do DFC at x is equal to 0. If I look at this one over here, the function, even though it changes, it's a piecewise function, even though it changes directions, it is continuous on a whole interval from negative infinity to infinity, so it's never discontinuous. So the next graph I have is one like this. Here, if I want to think of like patchwork, I could just patch that little hole, and then it would be continuous. It's still discontinuous at x is equal to 1, but it's a removable discontinuity. I'm sure I'm spelling everything wrong. I'm sorry about that. And then the next one, I'm looking at this graph here. This is a graph of a sine function, which if you think about sine, sine fluctuates between 1 and negative 1. Your domain, you learned way back when for your sine function, your domain is all real numbers. So there are no breaks, so this is a continuous graph. Remember, the graphs of sine and cosine are continuous, but the graphs of tangent, cotangent, secant, and cosecant are have areas where they're discontinuous. They have non-removable discontinuities. Now we're going to talk about one-side limits, and these come very handy for some real-life applications, and they just come in handy. So when I look at the notation, I made these really big so you can see this is the limit of f of x is equal to L. This plus sign means as x approaches c from the right. So the plus sign means that it's approaching from the right. So if this is c here, and I'm looking at my graph, I'm approaching from the right. So here's the right. I'm approaching from over here, and I'm approaching that point to see what the limit is. With the minus sign, this little minus sign means that I'm approaching from the left. So that would be red, left, and that means I'm coming from the left up until that point. So this makes it handy so that if I had a graph that looked something like this, here's C. Let's make this 1, let's make this 3. Open circle there, close circle there, and I have a graph that looks something like this. And I asked you to find the limit of f of x. Put that in the wrong spot. Limit of f of x as x approaches c from the right. So now I'm approaching this graph from the right, so I'm coming down here and coming from the right. I'm going to say that limit is equal to 3. If I ask for the limit of f of x as x approaches c from the left, here I'm coming from the left, coming up this graph, and I'm going to say that limit is equal to 1. So side limits can exist. So the limit as x approaches c from the right is 3. The limit of f of x as x approaches c from the left is 1. But if I were to ask you, what is the limit? If I were to ask you, what is the limit of f of x as x approaches c, and that means that as it's approaching c, that means it's not a one-directional thing, it's, one's from both sides. Since these two are not the same number, one's 3, one's 1, they are not the same number, that means the limit does not exist. So that's why side limits are important, is because sometimes it's important for me to know how the behavior is acting from the left and how it's acting from the right. even though the limit of C does not exist at that point. A great example of that is when I do the greatest integer. If I am approaching 0 from the right, so here's 0, x is 0. As I'm approaching from the right, I'm going back to color choice. I'm going from the right. As x approaches 0 from the right, I'm going to say that limit is 0. As I'm approaching 0 from the left, so I'm coming here approaching from the left, I'm going to say that limit is equal to -1. It's discontinuous at 0. It has a non-removable discontinuity at 0. It has a non-removable discontinuity at every integer. But I can find the side limits, which helps me. So as I approach from the right, it's 0. As I approach from the left, it's -1. So that's how side limits exist. If I were to ask you just to drill this in your head, as x approaches 0 of the greatest integer, you're going to say it does not exist. The side limits exist. The limit over all does not exist. And that's what this is saying. The only way you can have the limit exists is if and only if. This IFF means if and only if. If and only if the limit of C from the left and from the right approach the same number. If they approach the same number, then the overall limit of f of x as x approaches C will be the limit. That's the only in that. The reason why this is helpful is if I have this closed interval, I have a closed interval from A to B, from A to B. I have solid dots here, which means I have a value at A, I have a value at B. I can find the limit of f of x as x approaches A from the right, so I can find this, and I can find that limit to be whatever that number was. I can find the limit as x approaches B from the left, which would be right here, going this direction. But the reason why the limit of f of x at A does not exist is because I have nothing over here. There's no graph over here. There's no graph over here. So the plain limit as f of x approaches A does not exist. But from the left it exists, from the left to B it exists, and from the right to A it exists. And then, very important, see how since I closed my interval, I made it continuous in that interval. So what I'm going to do is if I look at something like this, which is a square root, a radical function, when I go to graph this, I know I'm going to have a very limited domain. And if I'm thinking about this, this 4 minus x squared has to be greater than or equal to 0. So 4 has to be greater than or equal to x squared, which means it's going to be 2 and -2. So that means my domain is x has to be between 2 and -2. And so -2 to 2. It's continuous in that interval. And that's what helps. That's what helps me about this is I know when I look at this graph, so something like this, I can find the limit as x approaches -2 from the left. I can find the limit as x approaches +2 from the right. But I can't find the limit of f of x approaching -2 from the left because there's nothing there. Nothing there. I can't find the limit as x approaches 2 from the right, because again, there's nothing there. But I can say that this function is continuous. F of x is continuous on the closed interval of -2 to 2. A real application is these two lovely looking gentlemen here. They talked about Charlie's law and absolute zero. Absolute zero is the coldest temperature that you can have with molecules. And summarizing, they can find out what it's approaching, because remember, limit is what it's approaching. But since absolute zero would be the lowest you can go, they can find the limit as you're approaching from higher temperatures, but they can't find the limit as you're approaching from lower temperatures, because in order for it to be the absolute zero, it would be the lowest temperature. So these guys worked on that. If you want to read it, it's in your book, just like a real life application. So now we're going to talk about properties of continuity. And I've learned that I need to go slow for these. So it says f and g are continuous at x is equal to c. So f and g are functions. So we're going to make f of x a simple function of just 2x. No, that's vector. Let's just make it x. And we're going to make g of x a simple function of, let's say, x squared. So if I have f of x, and f of x is a straight line, it has no breaks, it's continuous on all real numbers from negative infinity to infinity. If I take this f of x and I multiply it by a scalar, in other words, I now create a function that's 4 times x. I just made v equal to 4. That is going to be continuous from negative infinity to infinity, because this was continuous from negative infinity to infinity. If I take two functions that are continuous from negative infinity to negative infinity, and I add them or subtract them, so if I take x plus x squared, that is going to be continuous still from negative infinity to infinity. If I multiply them, so I have x times x squared, which will end up being x to the third, that will be continuous from negative infinity to negative infinity. It's still going to have the same continuity. The only time that you have to be careful is when you divide. So if I take x divided by x squared, I have to make sure that x squared is not equal to 0, because then I would have multiplication by 0. But other than that, it would still be continuous on the integral from negative infinity to infinity, except the one place where, so I could not do this for g of c, or g of 0, because then it would make the denominator equal to 0. That would be the only time it would change the continuity. Continuity composite function. So if I asked you the continuity of this, you would tell me that x is continuous except for x cannot equal 6. Here you tell me the continuity is from negative infinity to infinity. So when I go to do the composite function of f of g of x, so f of g of x, which is x squared plus 5. So now I'm going to do 1 over x squared plus 5. That's my x minus 6. I get 1 over x squared minus 1, which I can factor as x plus 1, x minus 1. So when I do the composition function, it's going to change my continuity. This function, this original function, was continuous except when x was equal to 6. G of x was continuous over all real numbers. When I do the composite function, I now create a new domain where x cannot equal 1 and x cannot equal negative 1. So now this composite function is discontinuous at x is equal to 1 and x is equal to negative 1. And those are both non-removable. I cannot simplify them out, and they will create asymptotes at those 2 points. So just seeing how the continuity changes when you take a composite function. Intermediate value theorem is probably the most important theorem you'll learn this week. All right, I'll say it this week. If f is continuous on the closed interval a to b, and k is a number between f of a and f of b, then there exists at least one number c in the interval ab such that f of c is equal to k. In English, if I have this graph, and let's say f of b, let's say that's 1, and let's say f of a is, say, 4. Let's say k is 2. I know it's not on this graph. Let's say a is 1. Let's say this b is 3, to make this 2. What they're saying is that if I have a value of 4 here, and I have a value of 2 here, and it's continuous, then I am going to hit every number between 4 and 2 when I travel along this path. I may hit some of the numbers more than once, but I'm going to hit every single number. So what it's saying is that there exists a number that when I say f of some number between 1 and 3, and I'm going to say that's 2, it's going to equal 2. So I'm going to hit every y value between 2 and 4 in the interval between 1 and 3. A better way to think of it is, think about when you drive your car. If I'm parked in my driveway and I'm going 0 miles per hour and my time is 0 seconds, and then I start driving to work, and 5 minutes later, I'm going 25 miles per hour, and I haven't stopped my car. I mean, I just hit the gas, started driving to work. Then somewhere between 0 and 5 minutes, somewhere in there, in that interval, it doesn't matter where, I have to be going exactly 10 miles per hour. Because to go from 0 miles per hour to 25 miles per hour, somewhere in here, I have to hit that 10. Does that make sense? I have to hit every single value between 0 and 25, between 0 and 5. That comes in very handy when I'm looking at a graph and I'm trying to find the zeros. So if I have this polynomial function, x cubed plus 3x minus 2, and I know that I am a continuous function, or the function is continuous between 0 and 1, and I know it's continuous because this is the domain of this function would be all real numbers. If I find f is 0, so I'm going to substitute in 0, so I'm going to have 0 to the third plus 3 times 0 minus 2. And when I do all that work, I get -2. When I substitute in f of 1, I'm going to have 1 to the third plus 3 times 1 minus 2, and that's going to end up 2. So between 0 and 1, my graph goes from -2 to +2, which means somewhere between 0 and 1, between 0, somewhere in the interval of 0 to 1, I have to have a 0. Oh, I don't want to say then. Somewhere between 0 and 1, f of x is equal to 0. Because at 0, I was at -2. At 1, I was at +2. Graphically, at 0, I'm at -2. At 2, at 1, I'm at 2. So if this is a continuous curve somewhere along here, I have to cross the y-axis. I have to, x-axis, that's the y. I'm at x-axis. Let's look at a trig one. So here I have x squared minus 2x minus the cosine of x. Cosine of x is continuous on the interval from -infinity to infinity, so it's continuous here. And then the function is continuous at x squared because that's a parabola, it's continuous. So I'm just adding and subtracting these. So I can assume that this function is continuous between -infinity to infinity. And that's the first point. It has to be continuous in the interval, and I'll show you an example why it has to be in a second. So I'm going to find f of 0. Substituting in 0, I'm going to 0 squared minus 2 minus the cosine of 0. So this will be 0 minus 2, and the cosine of 0 is 1. So I'm going to end up with -3. Doing the pi one, doing f of pi, I'm going to have pi squared minus 2 minus the cosine of pi, which is going to be pi squared minus 2, and then this is a -1, so this will be +1. So I'm going to have pi squared minus 1. Now, I don't really know what pi squared is, but I know pi is 3.14, and I know when I square that, I'm going to get something over 9, larger than 9. So larger than 9 minus 1 is still going to be something larger than 8. Do we all agree? So that's a positive number. This is a negative number. So I know I have to cross a 0 somewhere in between. The reason why it has to be continuous is if I had something like this, if I had a graph that wasn't continuous, and let's say I had this graph that went like here, and a closed circle here, and this was an interval from 1 to, let's say, 4. This is 5. Let's make this 2. Even though I go from 5 here to 2 here, because I'm discontinuous in this interval, I have this break in this interval, I'm not hitting all those values in there. That's why the first thing you have to do with the intermediate value theorem is make sure that your function is continuous before you can apply the intermediate value. Because in this particular graph, I'm not going to hit any values between 2 and 5. They're just not going to happen because I have that break in the graph. All right, here's your homework. If you have any questions from last homework, we'll catch up with that next class. Here's your homework for today. If you have any questions, email me. Hope this video was helpful.